which deals with valence bond theory. All right, so we have two theories we want to talk about in Chapter 9, valence bond theory and molecular orbital theory, because neither one by itself perfectly describes everything we can observe about molecular structure in the laboratory. So, starting with valence bond theory. So the valence bond theory approach is tied to Lewis's idea that there are electron pairs between bonded atoms. So we've drawn our Lewis structures, and we can draw nice lines between our bonded atoms, and those are the electrons that are shared. And there are some atoms in the Lewis structure that have lone pairs that are localized to a particular atom that are not shared between two atoms. So the orbitals from the atoms of a molecule combine to form a new set of orbitals called molecular orbitals. So we've talked about atomic orbitals that we see around atoms, and now we're going to mix those atomic orbitals to form molecular orbitals. So once we do the mixing, then the valence electrons that we have for each of the atoms that share the electrons in the bond, those valence electrons will populate the molecular orbitals. So we'll add those using the Aufbau principle for the molecular orbitals, just like we did for the atomic orbitals. So we'll start simple. The very first, the simplest, very smallest molecule is hydrogen, H2. So suppose we have two hydrogen atoms. Each one of the hydrogen atoms has one valence electron. So suppose two hydrogen atoms approach each other. And as they move closer, the electron in one atom is attracted to the nucleus, the positively charged nucleus of the other atom. So remember, each one of these atoms has a perfectly spherical 1s atomic orbital, but as the two atoms get closer together, their 1s atomic orbitals are distorted. So their electron cloud surrounding the atoms draws the two electrons toward a region of space between them. So that would form a molecular orbital. So then we form our hydrogen molecule H2. So we can draw a diagram that looks like this. So if we start here with our little story started over here, so here we show the two individual hydrogen atoms, and each one of them has a nucleus. So that's what that little black dot is. And they each have one electron, which is the probability of finding that electron is in that blue sphere. As they get together, though, we see that we develop a region of electron density between them. So that's the red. So red indicates an increase of electron density. So they get closer and closer and closer. And then finally, if we look down here at this energy trough, this is what happens when we have two hydrogen atoms, and they are of a certain distance apart, and here it happens to be 74 picometers, and the electrons in this red right here are shown between them. So this is the optimal, most stable distance for these two hydrogen atoms to be apart from each other. If they got any closer, then the nuclei would get too close, and the nuclei both being positively charged would repel each other. So here we have this nice, stable, lowest potential energy. That's our H2 molecule. The hydrogen atoms are of optimal distance apart, and they're each sharing that one electron that they each donated to the bond, and we have this nice red right here, this region of electron density between them, and that constitutes the bond. So we can illustrate this for other atoms too. So up here on top, this is the H2. So we have an overlap of two 1s orbitals, and this forms a bond called a sigma bond. So we can just think of sigma and single. So it's easy to do that. But these are what we call side-to-side overlap. Now we can make HF. You can draw a Lewis structure for HF. You drew it, I think, on your POGO activity, where we have hydrogen with its 1s orbital, and then the fluorine, remember, has 2p orbitals. It has 3 of them. So we have p orbitals on each of the x, y, z axes, but only one of them would overlap with the hydrogen. So that's shown over here just to show HF. So this shows the overlap of a 1s orbital from hydrogen and then just one of the 2 p's of the fluorine. And then that creates the bond between them. So the other electrons in the 2 p's, these are not shared and they reside just on the fluorine. Or we can make F2, and again, we'll have two fluorines, and they have, again, each one of them has three um, p orbitals and two electrons in each of them except for one, and that's why they need to share. So what happens is two of, of the p orbitals overlap end to end, and then they share that extra electron, and that's shown in this blue right here. So the overlap in these two p orbitals, one from each fluorine, and one of those two p orbitals only has one electron. So each of the fluorines each contributes one electron to that 2p, and now we have a bond, and that's the overlap. So that's another type of sigma bond. So these are sigma bonds, single bonds. They overlap end to end. I have to think about this. They overlap end to end, and we have a sigma bond, and it could be the different possibilities are two 1s orbitals, a 1s and a 2p, or another here we have two 2p orbitals. So each of them overlap end to end and form a single sigma bond. So again, more information about the sigma bond. Again, think sigma, think single. So it's a covalent bond that arises from the overlap of two 1s orbitals, such as in the H2, or in the other two examples. So in a sigma bond, the electron density is the greatest along the axis of the bond. And as I just showed you, sigma bonds also form when a 1s orbital like hydrogen overlaps with one of the p orbitals in an atom like fluorine or other halogens. And I did show you that halogens are bonded to one another by p orbital overlap, and that's an example of a sigma bond. Here's that same picture from a different textbook. I like this picture because it shows the individual hydrogen atoms right here, and the electrons are shown as up arrows of say +1/2 quantum number. But when we take these two orbitals and overlap them, those two electrons share electron density between them, and these have to be of opposite spin. So now this electron's one is drawn up and one is drawn down. So one has a spin of +1/2 and one's -1/2. And the same thing happens over here. So in the fluorine, again, we're going to have a p orbital on the y and a p orbital on a z. That's not shown, but those will have those lone pairs of electrons. But we have the 2p that's on the x-axis right here, and that contributes one electron to the bond, and the hydrogen contributes another, and then they share. Then that's their sigma bond. And again, those electrons have to be of opposite spin. That's shown for F2 as well. Again, there are p orbitals on the y and on the z-axis. That's not shown in this diagram. That's where the lone pairs are. But where that bond is between this end-to-end overlap of the two p orbitals on each of the fluorine. And each one of them contributes one electron. So when they form a bond, one has to be drawn spin up and one has to be drawn spin down. So valence bond theory, a summary is we have orbitals overlap to form a covalent bond between two atoms. And you have a bond consists of two electrons. They have to have opposite spin, and they're accommodated in the overlapping orbitals. And the bonding electrons have a higher probability of being found in a region of space between the two nuclei that constitutes the bond. And both electrons are simultaneously attracted to both nuclei in the atoms, which is what sort of keeps them there in that region between them. So this is a summary that I gave you when we were doing VSEPR theory. So what I want to do now is I want to give some examples of VSEPR theory and talk about how we apply valence bond theory to show how molecular orbitals form in each of these types of atoms. So starting here with a linear molecule. So we want to start with beryllium. So beryllium does not obey the octet rule. It's in group 2. So if you look at the periodic table and if you look at beryllium, beryllium has 2 electrons in a 1s orbital, but those are core electrons. Those would be electrons that look like helium. Here, we're drawing the electrons, only the valence electrons for beryllium, and beryllium has 2 electrons in its 2s orbital. So what we're going to do to form molecular orbitals is we're going to take one of the s orbitals and we're going to take one of the p's. Now there isn't anything in the p right now, but we're going to mix one s and one p and we're going to form two sp molecular orbitals. So this is how it works if I have an s atomic orbital and a p atomic orbital. I have one s and one p. That gives me two molecular orbitals. So they mix, so we call them sp, so we can show that it consists of one s and one p, and you always get the same number. So if I take two atomic orbitals and mix them, I get two molecular orbitals. And there's a picture shown right here. So the S is going to be a sphere, and the P is this dumbbell. So if we mix them, we form something that kind of looks like a dumbbell, but it's kind of big because it's the sphere. So here's our 2s orbital. We have one of those. Our 2p orbitals, we have one of those, and we mix to form two sp orbitals. But what we're going to do is we're going to draw sort of a more stylized version of it, and we'll what looks like this dumbbell right here with the little dumbbells on the inside that you can't see very well. But what I've done is beryllium, its nucleus is in the middle right here. And now it consists of two sp orbitals. So here's one and here's the other. And the way they distance themselves is 180 degrees apart because the beryllium has two regions of electron density. The farthest they can get away from each other is 180 degrees. So here's the 2s orbital, and it had two electrons, and the 2p, and it didn't have any. And I'm mixing a 2s orbital, one of those, a 2p orbital, one of those, and I get two sp orbitals, and here they are. And they look kind of funny. They look sort of spherical, but dumbbell, like one of the dumbbells is really big and was really tiny. Notice that we still have two additional 2p orbitals, but we didn't involve those in the mixing, so those are still there. So now when I want to make beryllium chloride, here's my beryllium, and beryllium's two sp orbitals are shown here. So here's one sp, so like the little one in the middle, that's not being shown. So here's one of the sps right here, and here's the other sp right here, and I have one electron here and one electron here. So I put one electron in one sp and one electron in the other sp. And then here's chlorine, and chlorine has a p orbital, so I'm not going to hybridize the p orbitals on the chlorine. And also remember that there's a p orbital here and a p orbital here, but we're not showing those because those are the ones belonging to the lone pairs of the chlorine. So when we form the beryllium chloride, what happens is this chlorine right here overlaps with this sp, and this chlorine overlaps with that sp. So here's our beryllium chloride, and there's the bond right there. So the electron going up was contributed by the chlorine, and the electron going down was contributed by the sp orbital in the beryllium. The same thing over here. So the sp right here contributes one and the chlorine contributes the other. So I have a single bond orbital overlap between those two, the sp and the beryllium, and the 3p and the chlorine. Again, remember there's chlorine p orbitals here and here, but we're not showing those because of those are the lone pairs. And beryllium also has two extra p orbitals that we didn't hybridize, and those are empty too. So if we just kind of draw our line across where we can see the nuclei, chlorine, beryllium, chlorine, and we can see the regions of electron density between beryllium and its two chlorines, we get this nice linearly shaped molecule. So I have a video that I want to show you that shows the formation of the beryllium chloride molecule. So let's start this. So there's the 2s and the 2p, and we're going to mix them to form the two sp orbitals. So it'll show that in a second. So again, we have two valence electrons. Both of them are in the 2s orbital. We mix them, so now we have two sp orbitals, and that's the shape that they look like. So that was the mixing of the spherical 2s orbital and the dumbbell 2p. So that's what it actually looks like, but then we're going to show kind of a stylized version. It's just going to be easier if we see that. And sometimes they even leave out these little bits in between. So what we did is we had two electrons, and the two electrons would have been in the 2s orbital, and the 2p orbitals of the beryllium atom, those would have been empty. So we put our two electrons there, and we're going to mix the 2s orbital and the 2p orbital. So we mix them and we form, okay, so now we have two sp orbitals, and now we're going to put one electron in one and one electron in the other. And we still have these two p's, but those we're not going to use those in our mixing, so we're just going to bring them aside. So now we have the hybridized beryllium with its molecular orbitals. So again, we took a sphere and a dumbbell and we mixed them to form this kind of weirdly, oddly shaped dumbbell structure. And we have one electron in each of the SPs. So here's our beryllium, and we mixed the orbital. So here, we haven't mixed it yet. So here the beryllium is still shown as an atom. So when we mix it, we want to do that because we want to form a molecule. So we want our atomic orbitals to mix. So we're motivated to do this because here comes two chlorines. So now we mix. So wait for it. There we go. Now we mix. There are two SPs, and we put one electron in each of the SPs, and then that electron will overlap with the chlorines, and then that's our beryllium chloride. So that's how the beryllium chloride forms. Okay, so that was beryllium chloride. So now let's go on and look at a molecule that has trigonal planar geometry. So let's look at boron. So boron has two electrons in its 2s orbital and one electron in its 2p. And remember, these are the valence electrons. We're not counting the cores. What we're going to do here is we're going to do a different kind of mixing. We're going to mix one s, and we're going to take two of the 2p's. So one 2s, two 2p's. That's three atomic orbitals. And I'm going to mix them to form three molecular orbitals. And I'm going to call those sp2s. Because I took one s and two p's. So I'm going to call those sp2s, and now I have three of them. Because if you take one 2s and two 2p's, I have a total of three atomic orbitals, as shaded in gray here. And when I mix them, I form three sp2 molecular orbitals. The other thing that I should point out that I didn't before is that the s's and the p's had different energies. When I do the mixing and I get the three molecular orbitals, all of them have equivalent energies. So when I mix the s and the two p's, I get, again, this kind of this weirdly dumbbell-shaped structure with a really huge dumbbell, with a little tiny dumbbell in between, like in here that they didn't show. And if I want to form the molecule BF3, then I put one electron in each of the sp2s, and then it overlaps with that lone electron on each of the fluorines. And again, this shows the overlap between the sp2 and the 2p orbital. So we didn't hybridize the fluorine. And also remember, there are other p orbitals on the fluorine, but those have the lone pairs. There's also another 2p orbital on the boron, but that doesn't have any electrons in it. So if we sort of follow the lines of the bonds and the nuclei, we have this trigonal planar kind of geometry, and the bond angles between these atoms are 120 degrees. So I'm going to go back to my video then and show you an animation of how this forms. So here's our boron. We have one electron and two electrons in our 2s orbital. And then we have a third electron in our 2p. So boron has three valence electrons. So we have one, two, three atomic orbitals. We're going to mix them and form three orbitals, sp2 orbitals of equivalent energy, and we're not going to involve the p. So we still have the unhybridized p. So we have a boron, and here the boron is shown in its atomic form with its 2s, with two electrons, and its 2p with only one electron. And it's not really motivated to mix until, okay, now three fluorines come in. Now we mix. So let's go ahead and mix, and now we're going to form the three sp2 hybrid orbitals. There's an electron in each one, and then we form the overlap between the one electron in each of the sp2s with the lone electron on the fluorine, and we form the boron trifluoride. So here is another slide of the boron trifluoride. And again, if you had drawn the Lewis structure, you'd put boron in the middle and you'd show this trigonal planar arrangement that it has. And here's a ball and stick diagram of it here and here. I got this from two different textbooks. So what's happened is that the boron has formed 3 sp2 hybrid orbitals, and then it overlaps with one of the p's of the fluorine. So each one of these is not drawn here, but it is labeled. We have 3 sp2 hybrid orbitals, and then there's one electron in each, and it overlaps with the one electron in one of the p orbitals, that unpaired electron in the fluorine, and the other electrons are in those other p orbitals that we don't show, and those are the lone pairs on the fluorine. So again, notice that boron is one of the elements that breaks the octet rule. We talked about that in the last chapter. So as I showed in the video, we take 2 s's and 1 p, and we mix them to form 3 sp2 hybrid orbitals. We take those 3 electrons and put 1 electron in each, and then here's the overlap between the sp2 hybrid orbitals, all 3 of them, each contributing 1 electron, and the fluorines, each contributing 1 electron. So we have single bonds, these are sigma bonds, and they form from end to end overlap between the sp2 hybrid orbitals on the boron and the unhybridized 2p orbitals on the fluorine. So let's move on to atoms that have a tetrahedral geometry. So let's specifically look at, we're going to spend more time on this because these are biologically important molecules. So we'll look at a tetrahedral molecule where we have a single central atom, and there are 4 bonds around that central atom. So methane is a good example of this. So what we do is we take carbon. Carbon has 4 valence electrons, and we have 2 electrons in the 2s, and then 2 electrons in the 2p. So what we're going to do here is we're going to take a 2s, and then we're going to take all 3 of the p's, even this one that doesn't have any electrons in it. So we're going to take 1s, all 3 of the p's, and since we have 1 2s and 3 2p's, that gives us 4, because you always get the same number. We're going to take 4 atomic orbitals and mix them to form 4 molecular orbitals. And since we had 4 electrons here, we're going to put 4 electrons in each one of these sp3 hybrid orbitals. And again, notice that the s and the 2p's had different energies, but I made 4 sp3 orbitals of equivalent energy. And then the way that the bond is going to form is we have 1 electron here, and hydrogen has 1 electron, so the hydrogen will contribute the other electron, and then we have the bonds between them. So that forms the methane. So let us go back to our video. So here we have a carbon atom, and we have 2 electrons in the 2s, 2 in the 2p. We're going to mix them all though, and we have 1 s orbital, 3 2p's, so we get 4 hybrid orbitals. We'll call them sp3s because it's 1 s and 3 p's. The 4 electrons go in each one. So here's our carbon. It's just shown as an atom, and we are not hybridized yet because we still have the 2 s's and the 2 p's. But when we come with 4 hydrogens, we get motivated to form the hybrid orbitals. So now we have the sp3s, and they overlap with the 1 electron on the hydrogen to form methane. Okay, so we're going to stop that here and go back to the PowerPoint. So staying with methane for just a second, there are lots of different pictures right here from different textbooks of methane. So we have our Lewis structure here, but remember methane forms a tetrahedrally shaped molecule, and we have 109.5 degrees between each of these hydrogens here. So this shows both a picture and a molecular model, and this shows the tetrahedron shape right here. So this explains why CH4 forms a tetrahedral molecule, because these bonds want to get as far away from each other as they can, and if you've got 4 of them, 109.5 degrees in a tetrahedron is how you accomplish that. So when we formed methane, as shown in the video, we took a 2s orbital and 3 2p's, even though we didn't have an electron here. We mixed 1s and 3 p's, and we formed 4 sp3 hybrid orbitals, and we call them sp3s because it's 1s and 3 p's, and there are 4 of them because we took 4 atomic orbitals, we mix them, and we form 4 molecular orbitals. and they all have the same energy. And then the carbon has the 4 sp3s, and then to form the methane, each one of the hydrogens donates 1 electron, and each one of the carbons with the sp3 donates an electron. And then we have a bond, 2 electrons in the bond. The electron density is between the atoms of the carbon and the hydrogen, and this again forms a sigma bond. This is end-to-end overlap of the sp3 hybrid orbital and the 1s orbital. All right, so we're going to stay here with the tetrahedron shape for a second here. Okay, so now I want to look at a molecule that's trigonal pyramidal. So its tetrahedron is its electron pair arrangement, but instead of 4 bonds, it has 3 bonds and 1 lone pair. So ammonia is a good example of that. If we draw the Lewis structure, we would draw it like this with the NH, with the bonds to 3 hydrogens and a lone pair right here. So we draw this as the tetrahedron electron pair arrangement. But if we look at the shape, because the shapes are determined by the nuclei, which are far larger than electrons, then we see that we have this trigonal pyramidal shape right here. So we have a tetrahedral electron pair arrangement, but a trigonal pyramidal shape. So this shows the big lobe right here of this electron, this lone electron pair. So let's look at how we would use molecular orbitals to describe the shape of NH3. So here, remember, nitrogen is in group 5. It has 5 valence electrons. We're going to do the same thing that we did with the carbon, in that we're going to take 1 s orbital and 3 of the 2 p orbitals, and we're going to form 4 sp3 hybrid orbitals. So it's the same thing, but remember that carbon had 4 valence electrons and nitrogen has 5. So when we mix these orbitals to form the 4 sp3s, we're going to form, we have to put those 5 valence electrons here in the sp3 orbitals, and we do the same thing that we do with atomic orbitals, where you fill them up singly before you start doubling up. So that's our lone pair right there. So that sp3 orbital, that's the lone pair, and that's not available for bonding. So instead of 4 like carbon, we only have 3 sp3 hybrid orbitals that are available for bonding. So here's the nitrogen. So we have 1 sp3 that can form an overlap with hydrogen over here, here, and here, and that sp3 hybrid orbital already has its 2 electrons in lone pair, and it's not available for bonding. So here we are. We're going back to our video, and here's nitrogen with it has 2 electrons in the 2s orbital, and it has 1 electron in each of the 2 p's. We're going to mix them to form 4 sp3 hybrid orbitals. So that's why we have the tetrahedral geometry. But again, now we have 5 electrons. Only 3 of them are available for bonding, and that filled one, that's where we have the lone pair. So here's the 5 valence electrons here. The nitrogen is shown as its atom, but now it's going to mix to form those sp3s, and 2 of those electrons are in the lone pair, and it's only available to form 3 other bonds. So we've just seen how nitrogen can form 3 bonds with hydrogen. Carbon could form 4, nitrogen can only form 3. And we see where that tetrahedral geometry comes from. It comes from the sp3 hybrid orbitals. But here, 2 electrons form the lone pair in one of those sp3 orbitals, and only 3 of them are available for bonding. So let us continue in our tetrahedral theme, and let's go to another molecule that has tetrahedral electron pair arrangement. But here we have 2 bonds and 2 lone pairs. So water is a good example of this. So I have a whole bunch of pictures of water. So here's our Lewis structure of water, and we would draw it at the electron pair arrangement, but we have 2 bonds and 2 pairs, which means the shape of water is angular or bent, and that's shown right here. Now we don't have 109.5 degrees. It's a little smaller because these big electron pairs are going to push these guys a little closer to each other than you normally find in a regular tetrahedron. But anyway, if we follow the shapes of just the nuclei, which are huge, we see this angular or bent shape for the water molecule, and then we have 2 of those 4 regions of electron density in lone pairs. So we're going to form sp3 hybrid orbitals here too, because we have a tetrahedral electron pair arrangement. So the oxygen atom has 6 valence electrons. Just like we did for carbon and nitrogen, we're going to mix one 2s orbital and all 3 2p orbitals. So we have 4 atomic orbitals. We mix them to form 4 molecular orbitals of equal energies. But since we have 6 valence electrons and we fill them up, and we do the same thing, we fill them up singly before we double them up. Now we have 2 lone pairs and 2 of our sp3 orbitals, and we only have 2 sp3 orbitals left that are available for bonding. So that means in the water, so what's shown here over here in red are the 4 sp3 hybrid orbitals, and 2 of them are overlapping with the 1 electron in hydrogen, but the other 2 are forming the lone pairs. So here we can see the tetrahedral electron pair arrangement, but if we follow the atoms, then we have a bent or angular shape for the water molecule. So let's go back to our video. So here we are with the oxygen. We have 6 valence electrons, 2s2, 2p4. We're going to mix all 3 of those 2p's and the 1s. We have 4 atomic orbitals. Now we have 4 molecular orbitals, the sp3's. We put those 6 electrons in them, and now we have 2 sp3's which have lone pairs and 2 available for bonding. So here's the oxygen in its atomic form before the hybridization takes place. Now here comes the hydrogens. So we're going to mix and form the 4 sp3 hybrid orbitals. 2 of them are available for bonding, and the other 2 form lone pairs. All right, so we finished the top row. So let's look at an example of a molecule that has trigonal bipyramidal shape. So these would break the octet rule. They can have 5 regions of electron density. And the example I want to show you is a molecule that has 5 bonds, so 5 regions of electron density, all bonds, no pairs. So let's look at PCl5. Okay, so phosphorus, if you look at its electron configuration, it has 3s2, 3p3, but we are in the 3rd period now, so we can borrow one of those d orbitals. So what we're going to do is we're going to mix 5 atomic orbitals. We're going to mix a 3s, all 3 of the 3p's, and 1 of the 3d's. And if we mix those, we're going to get 5 sp3d hybrid orbitals. So we have 1 s, 3 p's, and 1 d, so we call them sp3d. So we have 5 molecular orbitals, all of equal energy, and because phosphorus has 5 valence electrons, we can put 1 electron in each one of these 5 sp3d molecular orbitals. And now we can overlap them with 5 chlorines, and each of the chlorines will contribute 1 of their unpaired electron, and the rest of them will be in the lone pairs. All right, let's go back to our video. So here's our phosphorus. So we have 2 electrons in the 3s orbital, and we have 3 electrons in each of the 3p orbitals. So that gives us a total of 5 valence electrons for phosphorus. It's in group 5a. And we're going to mix the 3s orbital, all 3 of the 3p's, and 1 of the 3d, even though there's not an electron there. We're going to mix those, and we're going to form, from 5 atomic orbitals, we get 5 molecular orbitals. We're going to call those sp3ds, and we're going to put all 5 of those valence electrons, 1 in each one. So we've mixed them, and we have the other 3ds. Those are left over, and there are no electrons in them. So we're not going to draw them here. So here's phosphorus in its atomic orbital configuration before the mixing has taken place. So this is just phosphorus as an atom, but when phosphorus is going to form a compound, a molecule with these 5 chlorines, the mixing occurs. We get the 5 sp3ds, each with 1 electron, and then each one of them overlaps with each of the lone pairs on the chlorine. So here's our phosphorus pentachloride molecule. So each phosphorus, the phosphorates each has 1, 2, 3, 4, 5 sp3 hybrid orbitals. It overlaps with one of those unpaired electrons on the chlorine, and the rest of the electrons in the chlorine are in other p orbitals and serve as lone pairs. And here we see we have the trigonal bipyramidal geometry, where we have these three bonded pairs right here are in the a plane, so they're 120 degrees apart, and then we have these axial, one above and one below, and this would be 90 degrees apart. So this is how you would get 5 regions of electron density as far apart from each other as you could. So just as we showed in the video, we took 3s electrons, 2 of them, and we had 3s orbital, 2 electrons, 3 3p orbitals, an electron in each one, and we mixed an s, 3 3p orbitals, and a 3d to get our hybridized 5 orbitals sp3d. And the overlap occurs between this single electron here and then one of the unpaired electrons on the chlorine. Remember, chlorine has 7 valence electrons. So the other 6 are going to be in lone pairs around the chlorine, which isn't shown here. But that 7th one is forming a bond with with one of these unpaired electrons on the phosphorus. So these are sigma bonds, single bonds. They result from end-to-end overlap between the sp3d orbital and the p orbital on the chlorine. So this was an example of trigonal bipyramidal. We're not going to do these other 3, but you could do them the same way. All of these will give you sp3ds. It's just that not all of them will be in bonds. Some of them will be in lone pairs because they'll have additional valence electrons that won't participate in bonding. It'll be the same strategy that we used up here. So far, the blue is sp, the purple is sp2, the pink is sp3, the orange is sp3d. So now let us look at octahedral. What do we get here? So let's look at an octahedrally shaped molecule, and let's just look at an example where we have 1 central atom and 6 bonds. So let's look at sulfur hexafluoride. Okay, so sulfur has 2 valence electrons in a 3s orbital, and it has 4 in its 3p orbitals. And here we're in the 3rd period, so we're going to borrow 2 of our d's now. So we're going to mix 1 s orbital, 3 3p orbitals, 2 3d orbitals. That's a total of 6 atomic orbitals, all with different energies. We're going to mix them, and we're going to call them sp3d2. So 1s, 3p's, 2d's gives us sp3d2s. We get 6 of them, and they're all of equivalent energies. And again, we had 1, 2, 3, 4, 5, 6 valence electrons, so each one of these will go into each of the 6 sp3d2s, hybridized atomic orbitals, and again, we can form an overlap between one of those unpaired electrons in the fluorine. So here is the Lewis structure right here. So the sulfur right here will have 6 sp3d2 hybrid orbitals, and will form a bond with the fluorine by contributing. The sulfur will contribute 1 valence electron, and the fluorine will contribute an other, and these are the lone pairs. So let's go back to our video. Here is our sulfur atom. Sulfur has 6 valence electrons, 3s2, 3p4. So we're going to borrow from our d's, even though there aren't any electrons there. We're going to mix 1s, 3p's, 2d's, and we're going to mix those 6 atomic orbitals to get 6 molecular orbitals, all of equivalent energy. We're going to call them sp3d2s, and we're going to put each of those 6 valence electrons in each one of those equivalent sp3d2s. We're going to have 3 3d orbitals left over that we're not going to use for bonding. So here's our sulfur in its atomic orbital configuration with its 3s and its 3p's and one of its d's. And as a molecule, that's what it looks like. But if you want to form a molecule from this atom with 6 fluorines, we have the mixing, we have the 6 sp3d2s, and we form the molecule between the overlap between one of the electrons in the sp3d2 with one of the unpaired electrons on the fluorine. So here again is that same picture, mixing 6 atomic orbitals to form 6 molecular orbitals of equivalent energy. These are sp3d2s, they're shown in yellow, and the sulfur has 6 of these sp3d2s, which explains why it has the octahedral molecular shape, and then each of these 6 fluorines contributes 1 electron that's unpaired, and the other electrons in fluorine are the lone pairs. So this forms sigma bonds, single bonds, and it results of the end-to-end overlap between a 2p orbital on the fluorine and the sp3d2 on the sulfur. So, in the summary, if you have a linear electron pair arrangement, you form sp hybrid orbitals. So, linear, that's 2. 1s and 1p. Trigonal planar, you form 3 hybrid orbitals, sp2, 1s and 2p's. And you have a trigonal planar electron pair arrangement. If you have a tetrahedral electron pair arrangement, you form 4 hybrid orbitals. They're called sp3s, 1s, 3p's, and they arrange to form a tetrahedral geometry. If you have trigonal bipyramidal geometry, it's 1s, 3p's, 1d to form 5 sp3 d orbitals with 4 left over, and you form the trigonal bipyramidal electron pair geometry. If you have an octahedral electron pair geometry, it's 1s, 3p's, 2d's to form 6 sp3d2 hybrid orbitals. So this is going to be true whether those electrons are in bonds or in pairs, as we saw when I gave you 3 examples for the sp3. That's going to be true no matter what, if you have bonds or if you have pairs, even though bonds is what's shown in this table. Okay, so we're going to finish by looking at orbital overlap in single and multiple bonds, because you're going to go on to organic chemistry after you finish general chemistry, and this is going to be really, really important to organic chemistry. So I was trying to emphasize the sigma bonds, and the sigma bonds were end-to-end overlap. So everything I just showed you, all the bonds I just showed you, and all of those compounds, those are all single sigma bonds that resulted from end-to-end orbital overlap. What I want to show you now is I want to show you bonds that result from side-to-side overlap, and those are called pi bonds. So the way that it works is that if you have a double bond, one of the bonds in the double bond is a sigma bond and one's a pi bond. If you have a triple bond, one's a sigma bond and you have 2 pi bonds. So let's use ethane, ethylene, and acetylene to illustrate this concept. So this is ethane. We could make a model of this. I think we probably did a long time ago before spring break. So here are 2 carbons, and the 2 carbons each hybridize to form the sp3s, as I showed you for methane. So the way that ethane forms is that you have 2 carbons and 2 of their sp3 orbitals overlap. Each one of them contributes an electron. So we have 2 electrons, or 1 bond, between these sp3 orbitals, and that's a sigma bond. For the hydrogens, we also have sigma bonds because each of these sp3 hybrid orbitals overlaps with a 1s orbital of the hydrogen, and those are all sigma bonds as well. So here's the ball and stick right here that shows the tetrahedral geometry. So each one of those carbons formed sp3 hybrid orbitals, and then one of them, the sp3s on each carbon, overlap to form the carbon-carbon single sigma bond, and then the other ones left over formed carbon-hydrogen bonds. So we have single or sigma bonds there as well. Okay, let's look now at ethylene. So let's look way over here at its Lewis structure. So ethylene has the formula C2H4. There's a double bond between the two carbons, and then single bonds between the carbons and the hydrogens. So how do we do that? Well, let's look over here. Here the carbons form sp2 hybrid orbitals, because you can see over here the artist has drawn this, so we can see we have a trigonal planar geometry. So the way that we form one of those bonds in the double bonds is that we have an sp2 hybrid overlap between the two carbons, and then for the hydrogens we have sp2, the other sp2 hybrid orbitals overlap with the 1s orbitals on the hydrogens. But we have, when we do the sp2 mixing, remember we have a 2p orbital overlap. So that's how we're going to form the second bond of the double bond. We're going to, these p orbitals right here, these guys are going to overlap. So we'll have this overlap above and below, but it's just one orbital. So we're going to call this whole region right here, that's called a pi bond. So a pi bond is side to side. So these two overlaps are going to, these two p orbitals are going to overlap side to side. So in this double bond, one of these bonds is a single bond, a sigma bond from sp2 orbital overlap. The other is a pi bond from overlap of the sp2 unhybridized p orbitals. Okay, let's go back to our video now. So this is the Lewis structure of ethylene. So what we're going to do is we're going to show that it's this trigonal planar. So that means sp2, because that's 3 regions of electron density. So we have our carbon. We remember we still have 4 valence electrons. We're going to mix 1s and 2 of the p's. We're going to leave another p alone. So we're going to have 3, and we'll put 3 electrons here and 1 there. So we have 3 sp2 hybrid orbitals, each with an electron, and then one of the electrons is going to be in the unhybridized p orbital. So here we show 2 carbons next to each other as atoms, but now we're going to hybridize them to form the sp2. So there's the sp2. So we overlap the hydrogens, overlap with the sp2 hybrid orbitals, and then so we have the overlap there, and then we need 4 hydrogens. So we need, each of the hydrogens is going to overlap with 2 of the sp2s on each, but then that's the sigma bond right here. So that's an sp2 overlap between the 2 carbons. So that's a sigma bond, but there's our pi bond right there. So that's the p orbital right here. That's the side to side overlap. So there's our so now we can't rotate the way that they were showing before. So so the hydrogens will form, yeah, so if you tried to break, they would break the pi bond. So so in ethylene you can't break that bond, you can't rotate that. And if you drew a model, you could see that. So a double bond is 1 sigma, that's the sp2 orbital overlap, and 1 pi bond, which is the p orbital overlap. Okay, what about acetylene? Let's look at acetylene. Acetylene's formula is C2H2. There are 2 carbons and they're triply bonded to each other, and then we have bonds to hydrogen. So the way that this works is the carbon is going to be sp hybridized. Okay, so sp, linear, and when we hybridize the sp, if we pick an s and a p, we're going to have 2 p orbitals left over. So we're going to form a sigma bond, a single bond with sp orbital overlap here. But we have a triple bond, so these 2 p orbitals are going to overlap, and then these 2 p orbitals are going to overlap. So that's going to form the triply bonded carbon. So we have 1 sigma bond, which is end-to-end overlap, and 2 pi bonds, which is side-to-side overlap. I have just searched my video and they don't show acetylene for some reason. I'm sure I have a video with acetylene somewhere, so I will look for that and post it on Sakai. But again, to repeat, here we're just doing sp hybridization. So we have 1 sigma bond between sp hybridization of these the sp orbitals, we had a 2p orbital in this orientation right here. And we have another pi bond with these 2p orbitals shown in black overlapping side to side. And then in this orientation, we have the red 2p orbitals, and they overlap also side to side. So this is what our acetylene molecule looks like. So here we see it's linear. We have hydrogen, carbon, carbon, hydrogen. The triple bond comes between is formed between two carbons, and two carbons have an sp-sp overlap. That's where one of the bonds comes from. The second bond is a pi bond between the overlap of one of those unpaired 2p orbitals, and then the second of the pi bonds comes from the overlap of the other unhybridized 2p orbitals. So this triple bond consists of one sigma bond and two pi bonds. So this is a figure from our textbook here. So again, we have one carbon-carbon sigma bond. So in tan, those are the sp hybridized carbon atoms. This also shows the sp overlapping with a 1s orbital in a hydrogen. So that's where the carbon-hydrogen bond comes from. And then again, we've got two pi bonds. One of the pi bonds comes from the side-to-side overlap of one of the unhybridized p orbitals in one orientation, and the other comes from the unhybridized p orbitals in the other orientation. So a triple bond consists of one sigma bond and two pi bonds. So please do these problems in order to gauge your understanding, and I will see you next time when we will talk about molecular orbital theory.